Okay, so if we do not normalize these two, okay, I mean if we do not normalize using these two, and then suppose this x had a really large variance, and then yeah, so in the case of a correlation coefficient, suppose your data was perfectly in this linear shape, and then you have another data that have also like this perfectly linear shape. What was the correlation coefficient in these two cases? Both of them were 1. So it was not, yeah, it was independent on their actual slope, right? But that's because we normalize this covariance by using their own variances. So you can think of it as like, so x has the range, so x has the range as this a narrow range, and y also, y has this a wider range, right? So this can be interpreted as a some kind of indicator for our variable for x and y, but we are normalizing them, so we make them into a really a square, right? So we scale them up or down so that this length is the same as same as each other. So in this case, those correlation coefficients will be both 1. But if we do not incorporate these two, and then the numerator only will represent their slope, right? So that's how this guy or this measure is related to this slope estimator for our slope, which is beta. I mean, this is just an intuitive kind of understanding or interpretation. So back to this estimator for B. So this one is related to covariance. So when x changes, how big y changes, right? And if x increases and if y also increases, and then covariance will be positive and large value, positively large value. But if x increases and y decreases really fast, and then it will be negatively correlated, and then the slope will be really sharp or large, right? But in the case of correlation coefficient, we had these two normalization factors of the standard deviation of an x and y, right? And then you can think of this as just this. So we have the denominator now as the variance of an x, okay? So this corresponds to this denominator, okay? So that way we can extract out or compute this kind of slope, the measure for the slope between x and y, or this relationship between x and y, okay, but anyways, so this one is the variance of an x, and this one is the covariance between x and y. So that's how we obtain, by taking the ratio between them. That's how we obtain this slope estimator B. And then let's look at this A now. In this case, so among these points, what will be our x bar? So x bar will be the center point of our observations of an x, and y will be the center point of our observations in y, right? And then we just think of this virtual pair of x bar and y bar, okay? So intuitively we are fitting, given this x value, we are fitting this actual value with respect to by using this line. So that is our estimate of y, okay? And then we can think of some point or this two-dimensional point or coordinate that has x as x bar and y as y bar, okay, computed from, separately from this x and y, and then this point x bar comma y bar, so that point should exactly on this line, okay. And why is it true? So if we represent them as this, y bar is equal to a plus b x bar, because this can be moved to this, and then in this case we are having a error term as 0, okay. So that should be satisfied, and we have to adjust this. So we first determine the slope, and then this slope or this line should really coincide, or that should pass exactly the center point of an x comma center point of an y. So that's how we adjust this y-intercept or this a. So that is the meaning of this. Okay. And so, these are our results. So we do not explicitly plug this b with this complicated equations. Okay. And then now let's think about the distribution of our estimator a and b. So a and b, each of these a and b are the function of our random variable xi and yi. Okay, and then now let's think about the distribution of b and a. So we can think about the mean value or the expectation value of a and also expectation of b, and if the expectation of an a is exactly the same as alpha, and expectation of b is exactly equal to beta, and then we can think of a and b are unbiased estimator when these two are used for estimator for alpha and beta, right? So that was the meaning of this unbiased estimator, right? And so let's check if they are biased or unbiased estimator. And here, so even though I explained xi's and yi's are random variables, but here in this case we do not treat them as a random variables. So they are just a fixed given value from these tables, for example, like these tables where we have an x and y, and so on. So we do not treat them as random variable. So they are just a fixed value, and the only thing that we consider as a random variable is where is it? The only random variable that we consider is this epsilon I. So again, xi is fixed value, so they are constant, so they are not random variable, and this epsilon I is actually a random variable. And then this one is a random variable, and alpha plus beta xi, so this one is not random variable, and then altogether this one will form our yi, and yi is a random variable. Why? It is because this yi is a function of random variable ei. So that's why we view them. That's why we view this y as a random variable. But anyways, so I mean that's why we represent x as a lowercase letters and yi's as uppercase letter, because these uppercase letters are representing the random variable. But anyways, this epsilon I is a random variable. And then let's assume that this guy follows Gaussian random variable having zero mean and some variance. Okay. and then given xi, so suppose like xi was, for example, 61 in this case. In this case, alpha and beta, although they are unknown, but they are also fixed values, so they are not random variable. But our estimator are random variable, but the true parameters are assumed to be just a fixed constant value. So alpha xi, alpha plus beta xi. So up to this point is just a fixed value, although we do not know alpha and beta. And then if we add it with the epsilon I, and then it now becomes a random variable. And this one will follow. Yeah, so this one is something like this. So this one is our random variable, and then some constant. Okay, so we have a Gaussian random variable, and then we just like a shifting or adding a constant value with this random variable. And then this one will follow the mean as the Gaussian distribution with the mean as this fixed value, and then the variance will not change, right? So it is like x is following 0, for example, like 2 squared, and then what about 4 plus x? So this guy is n normal distribution with the mean of 4, and the standard deviation or variance will be the same, will remain the same, because we just shifted them. And so we have this random variable distribution for our yi. Okay, so you can now understand this expression, right? Okay, and then let's look at this derived result of this estimator of B. And then we have to compute this E of B, which is an expectation of B, to check whether B is an unbiased estimator of beta. Okay, and then we take the expectation of B, and then we take the expectation all in this part, but numerator is assumed to be just a constant value because it doesn't contain any random variable. And in this numerator part, the only random variable is yi. And so this expectation will be applied here, and then it will be applied only on this random variable. Okay, and then what is this expectation of yi? Since yi follows this Gaussian distribution, its mean value will be alpha plus beta xi. Okay, so we can just plug this guy into this part. And then we distribute them in this manner, Yeah, we have this denominator. And then, yeah, if we manipulate these equations further, and then we obtain this expectation of B is represented as a beta. So our conclusion is this B is an unbiased estimator of beta. Okay, and then let's think a little bit more on this equation. So suppose we are kind of a god, or we are oracle, and we already know the true parameter of an alpha and beta. So alpha and beta was like 3 plus 2xi. So suppose these are, let's assume that these are the true parameter. And what it means is given a so it's like this. So this is y equals 3 plus 2x, and so given this particular x value, so suppose this one is xi, and maybe this one is maybe 1, and then this value will be 5, right? And then this y will follow Gaussian distribution with the mean value of phi and then standard deviation of sigma squared. And then if we draw this probability density function in this plot, and then this one is fixed value, and then this one is mean value. Then the distribution, our probability distribution is defined over various y value. So the distribution will be something like this. Okay. So if sigma is really large, and then the distribution will be really like this, this guy. And so based on our true parameter, we only know the mean value as 5. I mean, even though we all know these full information of these true parameter, we only know the mean value. But since our yi's are involving this e epsilon I, which is a random variable, okay, so we can maybe observe some variables like this, or some variable like this, or some variable. Okay. Okay, so that way, yeah, we checked or verified this B is an unbiased estimator, and then we can think of this variance of this estimator B. So what is the meaning of the variance? So first of all, as an estimator, so again, B is an estimator for beta. So which one is a better situation or better estimator between the one with the small variance or large variance? As an estimator, is a small or large variance better? Which one is better between the small and the large variance? Yeah, the small variance is better. So what is, so if you remember our discussion about this variance of our estimator. So suppose our x is following the Gaussian distribution with the mu and maybe sigma squared, and then this is our unknown parameter that we want to estimate. And then when suppose we obtain the 3, 5, 4, maybe 7, 2. So in this case, we can obtain the sample mean by using these observations. And then that will be unbiased estimator. And then what was the variance of it? So it was n over sigma squared, right? The sample mean will have the variance as this, which means suppose this guy was maybe suppose this guy was maybe 4.5. So true parameter was assumed to be 4.5, and then on average, if you and then this sigma was maybe 1, and then on average, when computing the sample mean by using maybe 1, 2, 3, 4, 5, 6, 5 sample. So when computing this sample mean by using this 5 sample, and then you are expecting the error of your estimator or the difference of your estimator from the true parameter 4.5 will be approximately like, so the standard error will be like, it's like in the case of a standard deviation, we are considering this guy. So this guy is placed here, and this. So it is what? So it is like 1 over 2.2, and then let's say this one is 0.4, and then the meaning of this, or intuitive meaning of this, is your estimator or sample mean x bar. You have to expect that will give an estimator with the average amount of an error as 0.4. Okay, so in this case, sample mean was, what would be the sample mean? Maybe sample mean was 4. Okay, and then this guy was 4. And then in this case, this sample mean is on average, this estimator will be away, or this one will be different with the amount of 0.4 from the true parameter. So this is the meaning of this, the standard deviation of your estimator. Does it make sense? And this one is called also, this one has a special name as standard, not deviation, because we are talking about the estimator, and then we are talking about the potential or average error amount of this estimator, and so we are calling this as a standard error. So this one is actually the same as the standard deviation of your estimator. Okay, so in this sense, the standard error, if the standard error is small and then your estimator is a better one, you can rely more on this estimator as a true value. And if this error was if it decreases into a smaller and smaller value, and maybe suppose the standard error was 0.01, and then your estimator is expected to be a really close value to the true value, right? Okay, and then now you understood this the variance as the average error of your estimator, and then we discussed another estimator as a median, for example, like x median. So what is the median here? It is easy to obtain. So the median was 4. So it is just it became the same by chance, but suppose the sample mean was 4.2, and then this one is the median, and why not using this one as an estimator for the true parameter mu? And then we can also think of this biasness of this guy, whether this guy is a biased or unbiased, and then also we can also think of this variance. Okay, so in this case, variance is much larger than that sample mean. I mean, we can prove that, and so this one is a like a worse estimator than the sample mean. But anyways, you can think of this variance of this error as a average error. Okay, the variance of this estimator as the average amount of an error you have to expect when you obtain this estimator value. So that was a kind of a review, and this was because we wanted to understand why are caring about the variance of B, because B is an estimator of beta. Okay, and then variance of B is represented by this, and again this one is constant, and we have a variance only on the numerator part. Oh no, sorry. So we have B here, and we consider the variance of this guy. Okay, and then we have some random variable here, but some constant here in the denominator, and then the variance will be computed in a way that this guy can be factored out of this variance, but it should be squared, right? Because so it's like, suppose variance of an x was maybe 1, and then variance of 2x will be 4, right? So this one is squared, and so this guy is squared in this denominator, and the variance will be only applied in the numerator. Okay, then now this one can be viewed as variance of, let's just think of just 2, x1 and x bar times y1 plus x2 minus xy2. Okay, and then again only these guys are random variable, and then they are added together, and then we assume that they are independent, or EI's, or E1 contained in Yi, E2 contained in Y2 are independent. And thus, in this case, what about their variance? Variance of x plus y, if x and y are independent with each other, then it will be variance of an x plus variance of y, right? So we can apply this variance into these. Okay, and then on the variance of this again will have this random variable and also some constant. So we take this out of this variance, and then it will be squared, right? That's why we obtain, we see here, we see this, and then variance of yi, and then this, and then we have summation. And then what about this variance of yi? So yi, so what is the variance of yi? It is just a variance of ei, right? And so sigma squared, which is a, we may not know, so it may be an unknown value, but we know that this one is sigma squared. And then the remaining part will be here. So this one will be the variance of the estimator for our slope, right? And again, this one can be understood as a average error value when estimating the true parameter value beta. Okay. So it can be further represented by this, right? And this is a final result. And let's just try to understand it intuitively. So we have sigma squared in the numerator, and then denominator will be here. So what's the meaning of that? So the denominator will be like n times what? The empirical variance, right? Is it true or not? So again, it's like n times this guy over n minus x squared. So it's like n times the variance of x, which is an empirical variance. So again, if this variance of this estimator is small, and then it will be better because we can rely, our estimator would be like a more exact value, right? And then how do we achieve that goal? So it should be small value. And then if the sigma squared is small, and then if the sigma squared is small, and then it is more reliable estimator, right? And then what about this n? If we have more number of sample, and then it will be also good. And then what about this variance? If the variance of an x is large, and then it will also decrease our standard error or the variance of our estimator. And what does that mean? And why is it so? So it's it is kind of makes sense that small variance will lead to like more better quality of an estimator with a smaller error. And if we have more and more samples, and then our estimator will be also more reliable. And then what about this variance of an x? Can anyone give an answer or any guess on why? Okay, so it is a little bit interesting, at least in my personal opinion. So suppose I give you the 2 points, and then the 2 point was something like these two. And then suppose we have no error. So error was epsilon I was 0 in this case. And then, the slope will be easily obtained as an accurate value, right? So we can just perfectly accurately compute the slope, and that's the situation where this guy is 0, right? So yeah, that kind of makes sense. And then suppose we have some error, okay? So the true slope was something like this, but for this guy, it was found here by having this amount of an error, and then it was found here by having this amount of an error. And then our estimation for the slope will be, not surprisingly, this, right? Okay, and then so suppose the slope was 1, and this one was maybe 1 over 3. Okay, in this case we are like we are incurring a lot of an error between these two in terms of a slope. But suppose the range between these 2 points, I mean in terms of the ranges of an x, suppose our point was here and here, and then it was something like this, but it had the same error as here, and from here we have this amount of an error, and then the slope will be something like this. Okay, so as we can see, the slope is much closer to the original slope, right, given the same amount of an error. So if the interval between these x values are large, and then it will give a kind of an easier kind of situation to estimate the more exact slope value, right? And we are now considering the situation where many points are given. And what is the average distance of these many points? That is a standard deviation of an x, and then its squared version will be the variance of an x, right? So the variance will be can be considered as like average squared, like average distance squared. Okay. So that's why if we have a wider range of an x on average, and then we will have a small variance, which gives a higher quality of estimator for the slope. Okay, and then we can do the same thing on the A, so that, I mean, by checking there is a mean and also the expectation and also the variance. So if we consider this expectation, and then not surprisingly, we obtain easily this expectation of A is just a true parameter alpha, and thus it is an unbiased estimator. And then also its variance is represented in this manner. Okay, and then whose details are left as an exercise. So I ask you to derive this equation, maybe at home as a homework. But anyways, we obtain this variance of our estimator for the y-intercept. Okay, I haven't tried, but let's try to understand them in a similar manner. So if it is small, and then it will be good. And then if n gets large, and then it will give a better estimator. And then if it gives a large variance, and then also it will be like good one, right? And also if sigma gets large, and then it is a bad situation. And then interestingly, like this guy, what about this guy? Xi squared. So if xi squared, the sum of an xi squared is large, and then the y-intercept, I mean the estimator for y-intercept, it will be bad. And what does that mean? Can anyone give an answer? So the variance, the variance of an x is kind of an average like distance between the two data points, or from the center of an x. For example, suppose we had we had many x around here, and then the center point is here, and then on average with each of an x, the distance will be, the average distance will be the standard deviation, and as a squared version will be the variance. And then what about this guy, xi squared? And then it means, let's suppose we just added x by maybe 100, and then it will be like around here. It's like maybe it was maybe from 0 to maybe 10, and then it will be 100 to 110. So all x values are found here, right? So it is like a little bit of a zoomed out version, so that we have a really large distance, right? So this measure is considered as like the squared average distance starting from 0, not from its own center, right? This measure. And so if it is large, and then with while having the same amount of a variance, we can have that value as much as possible, as large as possible, by shifting them away from the origin, right? In that case, like we obtained these 2 points, and their error was around this value, right? And then let's move this guy here. Okay, so error was this, maybe error was this, and then suppose like this one is the estimated line, and then this one is our b value, and suppose the true one was something like this guy, and b will be, the true beta will be here. So if x's are away from the center, then their errors, right, the difference between the estimator and the true value will be magnified or amplified. And not magnified, but amplified, right? And that way, if this one is really large, and then the error of an estimator of A will be large. Let's see. Okay, so that's the interpretation of this variance of A. Okay, then the next topic is this guy. So it is called a sum of squared residuals, or sum of squares of the residuals. So what is the residual? So residual is, you can think of the error. Okay, so error means not the true error, but by using the estimated linear model. So instead of so if yi minus alpha minus beta xi, and then it will be exactly the same as epsilon I, right? But we replace, or we use an approximate model, or approximate this linear transformation, and then this one is the observed error, right? Observed error. So yi's are known, xi's are also known, and A and B are obtained as a particular value, and then their actual errors can be represented by this amount, and then we just take the square of it and then sum them up, and then it is sum of squares of residuals. And then what was this term? This term was, it is just the same thing as our the sum of errors, sum of squared errors, which we try to minimize. So we all started from this equation, right? And then obtained, set it, yeah, we tried to minimize them and then set their partial derivative with respect to a and b as, and then we obtained these equations, and that's how we obtained a and b, right? So after obtaining a and b, and then computing the resulting error value, okay? So that is the sum of squares of this residual. And then suppose a and b were obtained in this manner, and this one is the minimum value that we can achieve. Is it right? So we try to minimize that value, right? And then that's how we obtained a and b. And then we plug these a and b into this equation. And then given our observations, that measure will be the minimum one, right? The smallest one that we can achieve, right? It's just an obvious. But anyways, this one is called this sum of squares of residuals. And then, yeah, now we see some chi-square distribution in this case. And so, yeah, what does that mean? So, so sum of squares of residuals. So, yeah, let's understand this. So, suppose, yeah, let's consider this guy, yi minus this alpha plus beta xi. So we subtracted some these values, which are by using the true parameter, although we do not know them. Okay? So in this case, it is exactly the same as ei, right? And in this case, ei squared and sum over I going from 1 to n, right? So what is this? So this guy, ei's, each of ei's are following 0, comma, sigma squared, right? And then if we standardize it, since it is having a 0 mean and standard deviation as sigma, and then if we divide it by sigma squared, and then what will this follow? It will follow the chi-square distribution with the degree of freedom of an n, right? And now, yeah, so we understand that this guy is following the chi-square distribution with the degree of freedom of an n. And then, yeah, it is a little bit of a rough understanding without rigorous proof, but yeah, so you guys remember xi minus mu and sigma and squared, and then yeah, if xi is following Gaussian and maybe mu and sigma squared, and then this one I equals 1 from n, and then this one will be the chi-square distribution, right? xi n squared. But if we replace this guy as x bar, which is an estimator of the true mean value, and then it decreased 1 degree of freedom, so it is 1 degree of freedom, right? And that's why we obtain xn minus the degree of freedom of an n minus 1, right? And then altogether, we are estimating the mean of yi by using the two estimator of a and b. So you have now 2 degrees of freedom that can change your they can maybe replace the true mean value of y into an approximate one to just minimize this error part. And that way, this one eats up like 2 degrees of freedom. And thus, this measure, when replacing this one as a and b, and then this one will be following the chi-square distribution with the degree of freedom of n minus 2, because we are using 2 estimators. Okay, so that's it for today, and yeah, let's continue next Tuesday. Okay, thank you.